Over the next few decades, the world's population is set to increase as never before, passing the 9 billion mark by 2050. A world with so many people in it means a huge increase in energy demands, even if we learn to use supplies more efficiently. So we must find ways of producing more energy, and soon. The damage to our environment makes fossil fuels an unattractive choice. And whilst nuclear fission and renewables such as hydro, wind and solar energy are major non-carbon options, they alone can't produce enough. That's where fusion comes in. Fusion copies the reaction that powers the sun. We fuse two forms of hydrogen, deuterium and tritium, together to make helium, and a spare neutron emerges with 1,000 times the amount of energy that went in. To make this reaction happen on Earth, we have to exceed the temperature of the sun, over 100 million degrees, confine the hot gas of fuel known as a plasma within a magnetic field, and contain it at the right density and temperature long enough to sustain fusion, and therefore produce energy. To do this, we use a magnetic container known as a tokamak. At Culham Centre for Fusion Energy in Oxfordshire, we've been making fusion happen for over 20 years. Culham hosts the world's largest tokamak, JET, the Joint European Torus. We operate JET for scientists in over 20 countries under the European Fusion Development Agreement. At JET, physicists and engineers are proving the technology that will be used for ITER, the world's first tokamak experiment to produce power on an industrial scale, currently being built in France. Most fusion research so far has concentrated on tokamaks with a ring-shaped plasma, such as JET. But the UK fusion programme is at the forefront of research into a newer, potentially more efficient design, the spherical tokamak. The first spherical tokamak, START, designed and built at Culham, produced such impressive results that approval was given for a larger project, the mega-amp spherical tokamak, MAST. Spherical tokamaks are more compact devices, and less magnetic field is needed to contain the plasma and keep it stable, meaning better efficiency and better plasma performance. MAST also has an extensive range of diagnostic equipment, which is helping researchers to understand in more detail how plasmas behave, whilst high-speed cameras operating at up to 250,000 frames per second make MAST the only tokamak in the world to produce images of the whole plasma for study. With world-class research in plasma theory and modelling, materials development and technology for power plant designs, the UK fusion programme is forging ahead with research, not just to help prepare for ITER, but to design systems for the fusion power stations that will follow it. MAST started operation in 2000, and now a £30 million upgrade is underway. By 2015, the new MAST will be equipped to run longer, higher-powered experiments. This will enhance all areas of the UK's fusion programme and open up new opportunities for other laboratories and universities to collaborate.
You know, we're doing fusion on JET, and ITER will come along and it will do fusion at the scale of a power station. The goal is not just to do fusion, the goal is to put fusion electricity in everybody's home. And what the MAST program is about is to bring the cost and scale of the fusion devices down to a point at which we can produce affordable electricity.